Okay, welcome back to our next installment. This video will cover section 5 of topic 10 of the IB curriculum, covering halogenoalkanes. Now, in section 1 and lecture and class, we talked about classes of compounds, and the halogenoalkanes, if you remember, were alkanes, which were carbon-to-carbon single-bonded compounds, such as this one, which would be propane. And there would be one or more halogens attached. So if we put a chlorine on this here, remember each carbon has an octet, and so we can symbolize those hydrogens as such. So when the halogen is present, we have to indicate its location, its presence, and its location. In this case, this chlorine is attached to this carbon, and remember we start numbering from the end closest to the functional group. So this, in that case, is carbon 1, not 3. So this compound would be named 1-chloro, and because there are 3 carbons, it's propane. The ane refers to the functional groups present here. Now, with halogenoalkanes, we're going to get into some organic chemistry that's probably the most difficult for the standard level curriculum. You can see that here in the points here. It's talking about substitution reactions and these funny looking little symbols here, this SN1 and SN2. So we're going to take a little time. This video may have to be broken up into 2, just so we can get the complexity necessary to handle these. So just make sure you understand how the naming system works. If you have questions, you should go back and preview some videos on naming. Another thing here that I feel we need to get up front, or get out of the way up front, is has to do with this word here in that curriculum point, in that assessment statement, that of substitution. In a previous video, I believe it was the video covering alkanes, we introduced an addition reaction very quickly, or perhaps it might have been in the alkenes video. So let's go ahead and review that quickly. If you remember, for alkenes, that refers to a double bond. So we're going to use ethene as our example. Remember, ethene can undergo several different reactions. That second bond is fairly reactive relative to the sigma bond. The second pi bond is relatively reactive relative to the first hybridized sigma bond. And one of the reactions that this can undergo is a reaction with a sorry, lost my train of thought there. With a compound like hydrochloric acid. And the issue here is that the compound we're adding here is added across the double bond. So the highlight here, and what I'm trying to stress to you or remind you of here, is what an addition reaction is. And in an addition reaction, our original compound and the added reagent will combine. There will be no byproduct. So here what we're going to have is this hydrogen and this chloride adding across this bond, so that if I include the original compound in black, we have that, and then if I add the added hydrochloric acid here in red, we'd have that. Notice that both compounds are combined. This is an addition reaction. And the name of this would be chloroethane. The number 1 is irrelevant. It's redundant, not necessary, because as long as there's one chlorine, it has to be carbon number 1. So the key point here is what an addition reaction is. The reactions we're going to be discussing in this section are substitution reactions. And in a substitution reaction, we're going to exchange one thing for another. So I'll try to make a very basic example of a substitution reaction. So a single displacement reaction would be an example of such thing. So notice that the compound A, generic compound A, has displaced or replaced. So this is a substitution reaction. So just as we're going through these examples, just try and see why it's called substitution, and compare it in comparison to those reactions with the alkenes, which were addition reactions. So you can see up here, we'll also be including the compound sodium hydroxide, and I'll tell you where that fits in the next few slides. So let's go ahead and move forward. So we're going to focus on the first one. We're going to focus on substitution reactions of halogenoalkanes with sodium hydroxide. And I'm going to start off fairly simple. And what we're going to talk about is the properties of halogenoalkanes and sodium hydroxide that grant them this capability. So I'm going to start with a very simple halogenoalkane. We have to do a little bit of establish some rules here. Now, this drawing is a two-dimensional drawing, so it appears that the angle here, of course, is 90 degrees, but we know that it's not. It's in fact 109.5, and that comes about because the two-dimensional drawing fools us. But remember, we have a central atom here surrounded by 3 pairs of electrons, and they will take positions to, 4 pairs of electrons. They will take positions to maximize their distance from one another. And in three-dimensional space, that maximum distance is an angle of 109.5. But it's very difficult for us to show that in a drawing such as this. So I'm going to attempt to do so with the introduction of a little bit of symbolism here. And what we're going to do is we're going to use some arrows, some triangles in a little different way. So let me see if I can explain this. In my drawing, I'm going to recreate this drawing, and I'm going to leave this bond and this bond in the plane of what looks like the paper here. So those bonds are on the same plane as the paper. Now it's these two that would be slightly different. One of them would be going back into the paper. One of them would be coming out of the paper towards us. So I'm going to symbolize the one coming out of the paper towards us with a triangle that is solid. Understand that that's coming out towards you. And then I'm going to symbolize with a triangle with, it's not very starboard isn't very conducive to this drawing, but I'll do the best I can. It's supposed to be a triangle, so let's just say that we'll use dots symbolizing a bond that goes back into the board away from us. So it's going to take a little bit of imagination. It is a limitation of a two-dimensional surface. But you have to understand that this is a more representative drawing of the three-dimensional structure of chloromethane. Now, let's get to some more of the information here. Now, in a normal, I shouldn't have said normal, in the process we called chlorination or halogenation of alkanes earlier on, it was a previous video. I believe it was the alkanes video. It was a chain reaction type of process. And so just reminding you, that process began with a halogen similar to chlorine, and in the process or in the presence of ultraviolet light, it is possible to separate those chlorines into form what are called free radicals. So in that video I explained that what was really occurring here, and here is the chlorines before being separated, that the ultraviolet light, the energy from it, was enough to split this bond equally. So you can see one of the pair is now here, the other of the pair is there. Of course, the unshared pairs are still present. We typically don't talk about them, but this single electron, or you could say this outer shell with one missing electron, makes a very reactive molecule called a free radical. And that could react further with others, and actually it could do a substitution reaction. So if you look back at that video, we could react that free radical now with ethane. Excuse me, I need to put the dot here. We could react that with ethane, as you see here, and it could pull off the H, one of the H's, we'll just assume this one, and in the process leave behind a free radical version of ethane. So in this case you can see we have two things combined. We end up with two things at the end. We don't combine them. So this is an example of a substitution reaction. We are substituting something in place of something else. Now it's not typically an atom, or it's not an atom we're substituting in this case, but nevertheless the format is similar to substitution. We are not combining two things. We have two things coming in together and two things come out. so that we'll see that in the substitution process. But back to what I was trying to get across here. This process splits this bond equally, and so this is called homolytic fission. Remember, the prefix homo means same, or I guess you could use it to mean equal, but typically it's used as same. So it splits that equally. Now, the situation is slightly different in this case. And we're going to focus on this bond right here in this halogenoalkane. Remember, here in this chlorine compound, that bond is very nonpolar. Each chlorine has an equal electronegativity, therefore these electrons are shared equally. So the splitting of this bond, it makes sense that the residual electrons would be evenly split. But in this case, this bond is polar. As a matter of fact, it's polar in that direction towards the chlorine. So if that bond were to break, it's very likely to break and leave chlorine with an extra electron, negative ion in that case, and leave behind, in place of it, if you look carefully here, that would leave behind the residual compound. Now, there would be a problem here, something we need to consider. Now, this carbon now only has, first of all, a central carbon with 3 bonded pairs. Remember, both of these electrons in this bonded pair left, leaving a carbon here, central atom with 3 bonded pairs. So if you remember our symbolism back in the Vesper theory unit, this would be AB3 symbolism, which is trigonoplanar 120-degree angles. So in addition to that, this compound also has a positive charge because it took an extra electron away. Chlorine left with an extra electron, so this made left behind a positive charge. Now this is a very important part of this. Let me recreate this or redraw this down here because I really want to emphasize this. That compound where we have this H is now in the plane of this paper, and I can actually draw them. I'll turn it on its side so it faces us, so they're all on a plane now. This is a positively charged carbon. This has a name. It's called a carbocation. Extremely reactive. That's going to play a big role in our upcoming unit here in this upcoming video. And the reason, remember, for leaving this behind, is that original bond broken here was polar, and the electrons were closer to chlorine, so it makes much more sense for them to take it with it. Now, so if you've been paying attention in class, something that is a product that is extremely reactive is very unlikely to form. It would not just happen spontaneously. Something would have to contribute to its formation, or it's the combination of it with yet another compound, yet another reagent. If the product of that reaction was so much more stable, which released so much more energy to pay the cost of the formation of this, then I guess it's possible. But in a really basic sense, the formation of this is not very likely. And if it is formed, it is very short-lived and extremely reactive with everything around it. But nevertheless, it does form the basis for this section. So, a little bit more vocabulary. Remember, this group, chlorine was attached, it left, and therefore we give it a name. It's called the leaving group. Leaving groups tend to be highly electronegative compounds, like chlorine. Remember, they leave with that extra electron. It's a heterolytic fission, leaving behind a carbocation. However, the carbocation doesn't really want to be formed, so there had to be something that caused it to occur. So there are compounds which can initiate this process. Those compounds are called nucleophiles. These are compounds that have unshared pairs of electrons. Some common nucleophiles are cyanide, hydroxide, and in some cases halogens, but we're going to focus on these two. And I think this is the one that specifically IB wants us to know. So if we were to draw the Lewis structure of this compound,